Hello and welcome back to my Physical Science online video lab supplement series. Today's video is going to be a walkthrough video of the periodic motion of a spring oscillator, um, for short the Spring Oscillations lab. Also, because the university is requiring of us a formal lab report for all of these general studies labs, this is the lab that I have selected to inflict that upon you all, um, on behalf of Troy University. So my apologies in advance. Um, I will, however, more seriously be using this as the um, also walk through on how to do the formal lab report the way that Troy University has dictated that it must be done. I should state in advance that the rubrics that they've handed down have in fact been handed down without much in the way of real consultation of faculty. What that means is I have basically nothing to do with this requirement that you need to write up this formal lab report. However, we are writing these up as sort of like a part of our accreditation as a university. So in that sense, it is important that they be done. This lab, because it has a formal lab report attached to it, is worth different than the other labs that you've done, and it is graded differently as well. Instead of doing the lab and then just taking a quiz afterwards, for this lab, you will do the lab, write up your formal lab report, submit that to me via Canvas, and then that is what's getting graded this week. And there's no lab quiz because, frankly, this is going to be more work than any lab quiz would have been. So in some sense, you could think of this as being sort of like the equivalent of your midterm exam for your lecture class, in as much as this is the thing that's going to have a lot of weight to it. All right, so let's resume then with our instructions for the lab. All right, so I've pulled up here the report guidelines for you. Let's move them over here and get this like this so you can see them. So basically in this experiment we're going to be using more or less the same supplies as you used in your previous experiment to build the Hooke's Law spring. That is, I think the experiment we titled it Building a Spring Scale. Okay, so that was this experiment right here. And you'll recall in the handout that I gave you a list of suppliers for finding a simple spring. You could go to Pasco Scientific, you can go to Vernier Scientific, you can go to Amazon, you can go to Fisher Scientific. There are other suppliers, of course, as well, but this is sort of a list to get you started. Then on the top of that, you needed a set of masses. So you could use fishing sinkers, slotted weight sets, or something like washers and nuts. And again, what I ended up using was just a simple set of these washers like this. And then I had some springs that I had bought from Amazon, but the specific supplier was this ISCO Labs Hooke's Law spring set. Okay, so that is what I used when I did building a spring scale. That is also what I am using in today's lab. Okay, so equipment wise, what you're going to want to have is some springs. I have for myself a set of 3 springs. Let's look at them here. Okay, and each of those three springs has some slightly different properties, and then you have to have some set of weights. So I have a set of washers here. So these are just plain old washers that I bought from the hardware store to use as weights. It can also be helpful to have something to attach the spring to, and maybe some string like this to hook stuff together just for convenience. Last but not least, if you are using fishing sinkers, maybe you already know what the weight of the sinkers is each. If you're using a slotted weight set, you do know probably what the weights of those are in grams. But if you are using something like washers or nuts and bolts from Lowe's, you may want to have a scale um, to use for getting the mass of the weights. Okay, so I have a scale here for that. And then for today's lab, different from what you had in the Hooke's Law lab, you will need some sort of stopwatch, which I'm going to be actually just using the stopwatch that's built into my phone. And you will be needing to have a ruler, although I guess you had that in the spring lab in the previous spring lab as well. The ruler really is just to make sure that we are not introducing extra variables by changing the displacement each time. My stand actually has a built-in ruler to it, so I'm actually going to make use of that, but for most of you, just some sort of a standalone ruler like this is obviously adequate. So okay, so let's look at what all you're doing in this experiment. Basically, you have some background information from your previous experiments. We've already done a Hooke's Law lab where we test how much force this spring or whatever spring you're using applies versus how much it is basically stretched from equilibrium. Again, warning with these springs, especially these ones from ISCO, if you put too much weight on them, they will overstretch, and that will actually change the properties of the springs. I have in fact actually done that to the shortest spring in the ISCO set that I bought off of Amazon. It will still work just fine as a spring. It's just no longer going to have the same force constant as it had when we first got it. Okay, so in the previous lab, you found, hopefully, that the amount of force that the spring is applying is linearly proportional to the amount that it is stretched by. So that basically means if I stretch the spring out by 1 centimeter and it applies 1 Newton, then I expect the next centimeter to require another Newton, and the next centimeter to give another Newton, and so on. With, of course, some possible offset for internal tension. And as it turns out, the springs that I have right here do not have internal tension. They are, in fact, all three compressible, and that usually means zero internal tension when there's no weight attached. So my springs actually follow this. The springs that you get may follow this, or there may be a plus some internal tension force that is a constant value in the equation. Okay. Now, what we want to do, the basics of this experiment, and I'm going to kind of re-aim the camera a little bit, I hope. You can see here is my stand. I'm going to hook up my spring right here, and I'm going to take some amount of weight like so, and I'm going to attach it to my spring. And so to do that, what I will do is just kind of loop this little string through the centers of all these guys, and then basically I need to use the little hook area on this spring to attach the weights like so. Whoops, there we go. Okay, and as expected, the spring is stretched out somewhat from what it was when there's no weights attached. So you can see it's a bit longer. I have a little scale here that can be read. I'm going to turn it around so it's facing me, and then kind of read it off. Mine's kind of fancy. It has a little mirrored surface on it, by the way. So what I do is I just look at the reflection in the mirror and see where that lines up with the scale. And then essentially it's lined up with the 4 centimeter mark from my position. And so what I do is I grab onto the weights and I pull it down by, say, another 2 centimeters. So now it's lined up with the 6. And then what I would do is I would release it and let it oscillate up and down. So before we get into timing stuff, one of the things is, what exactly are we timing? The answer is complete oscillations. So if I release it, it's going to go bouncing up and down. You can see it bouncing up and down here. It's also swinging back and forth, which is not so good. We really just want it to bounce up and down like this. And then as far as what is an oscillation, I'm going to just manually move it up and down to sort of simulate the oscillations for you, so that you can see what's going on. So I've pulled it down and I release, and as I release it starts to rise up like this. So it kind of comes up. This right here is the actual equilibrium position. Means that the net force is 0 on the system. Gravity is pulling down, the spring is pulling up. And it actually will pass through that equilibrium to something like this. So if I pull it down by 2, it should bounce up by 2 above the equilibrium, more or less. Okay, and so basically if I've pulled down here and I release, it comes up, comes back down, and then starts to turn around and come up. So that is one oscillation. So from here back to here, from here up to here, back to here, that's one oscillation. So what you want to do is count how many of those take place in a given time, or alternatively, you can count up to a certain number of oscillations and see how much time has elapsed. All right, so what I'm going to do here, I'm going to open up my phone and go to the stopwatch function. Okay, so we've got our stopwatch function ready. I'm going to pull this down and I'm going to release and start the timer, and I'm going to count out 10 oscillations and then stop the timer. Okay, so ready, set, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, and then I have a time to complete those oscillations. All right, so in this case it is 4.9 seconds for 10 oscillations. All right, so what I would do for this experiment, that what I've just done is basically the complete example of maybe one whole measurement. Okay, and so what we do from here, we have several independent variables here that we can change. You can change the spring that you use. If you have multiple springs, you can change the spring that you use. So that basically means you're changing the spring constant. You can also change the amount of mass attached to the end of the spring. In other words, I could add more masses or take some masses away. And then you can also change how much you displace by. So I displaced by 2 there, maybe I do by 3 the next time. Whoops, that's not very good. Maybe I pull down by 3 so that it's at 7. And then I just release 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And unfortunately with my setup it has a tendency of swinging. If you want it to swing less, Sometimes you can attach if another string up here, and it will tend to reduce the amount of swinging if you've got just a spring on a smooth metal surface. But it's very difficult to get rid of all of that. Um, so you're going to make each of those changes sort of one at a time. And basically what you want to do is see which of those things causes the period to change. Okay, so by pulling it down farther, does it take more time or less time? And you may have to do more than one iteration. It may be, given that you have a reaction time as you measured in lab 1, it may be that you need to repeat this, let's say, 3 or 4 times before you know for sure that yes, pulling down is by more causes a longer or a shorter period. Or alternatively, that you know for sure that no, pulling down by more does not change the period. Okay, so that is item 1. Then you go on to item 2, which is what happens if I change the mass out. Okay, so I put this guy back on, and instead of having this much mass, maybe I add some more mass to it. Oops. Now I have this much mass. Okay, so now I attach all this to the same spring, and I'm going to want to hopefully use the same 2 centimeter initial displacement from equilibrium. Although, as you can see, that may not be feasible because now my masses are nearly touching the base of this. Okay, so maybe you should see when you've attached all the masses you're going to use, do you have space to pull down by that 2 centimeters? And now I can always take some more masses back off, and that will let me maybe keep my 2 centimeter initial displacement. Okay, so put this guy back on, attach it back up here. Now I've got room to do a 2 centimeter displacement. Okay, so what I would do is pull down to 2 centimeters, which is right here. We're pretty dang close to hitting the base. And then again I would release and I would time it. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, and now we look and see what the time is. And in this case, it turns out it's a different time than the previous. Okay, so that is the experiment for that part. Then for the last part, what you would do is essentially change out the spring and maybe repeat your. I guess you have 2 options. One is if you have a lot of springs, and I only have 3 here, but I could link them up in series to make more if I wanted. There's, I guess, 6 combinations here, and that's getting close to the right amount. So I could do that. Or if you don't want to mess around with trying to figure out spring constants for lots and lots of springs, what you can do is, having gone through and got the data for one spring, you go through and get it for the next spring, and it's really just the same data again. So again, you would do the mass attached to the spring. The spring is, I happen to know, is a little weaker, so I'm going to use less mass because I don't want to overstretch it. But see, I'm even with this little mass, I've actually, you can hear it clanging down there. I've already hit the tabletop. So it's, too much mass already. But you would change how much mass you're using again, and again you would need to uh, find maybe 7 or 8 data points worth of mass versus period. So I pull down and I release 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'd stop my stopwatch, add a little more mass, etc. Okay. So that's the experiment itself. Some additional things that you will need to do in order to make this experiment work out. First of all, like I said, if you happen to be using something like this as your mass set, you will need to figure out how much mass each one of these has. So if I put this one on, this says 6.9 grams. If I put this one on, this one says 6.9 grams. 6.8 grams. 6.9 grams. 6.9 grams, etc. So you'd want to mass them and make sure either do they have the same amount of mass each time, or if not, how much mass does each one have? Maybe put like a little mark on it with a permanent marker to keep track of it, so that you know how much mass is at your spring at any given time. So I can put this on here. It says 13.9 grams for these two. So I have 13.9 grams worth of mass oscillating on the end of this. If I put another one on, maybe I have 21 grams or something. Okay, so that's sort of the quantitative side of the experiment. There's some additional stuff that you're going to end up having to do here. For one thing, you ultimately want all your numbers to be in kilograms and meters and seconds. So the times that you're recording on here are already in seconds on your stopwatch. But for your masses and for your stretches, you may have to do some basic unit conversions. So I will do it this way, and then I'll also show you how to do it on a spreadsheet, because it may be beneficial in this lab's case to do stuff on a spreadsheet, since you're going to end up needing to generate a graph and turn it in, and that's going to be easier on a spreadsheet. Okay, so let's see, where's this? Okay, so I said earlier that I had pulled the masses down by an initial displacement. We could call this delta x initial of 2.0 centimeters. Okay, so we want that in meters. So we have to multiply by how many meters per centimeter, or vice versa. So you know, or should know, that there's 100 centimeters. Centa means hundredth. So 100 centimeters in 1 meter. So the meter goes on top so that we can cancel the centimeters. Okay, so I got centimeters here, I've got centimeters here, those cancel. And so I'm left with only the unit of meters. 2 divided by 100 comes out to 0.02, and I realistically have a significant figure here, so I can write something like this. Oops, except that I'm writing the wrong unit. It's 0.020 meters, not 0.020 centimeters, 0.020 meters. Okay, the other unit conversion is that the mass, so I'll write it out. This was initial displacement. Initial displacement from equilibrium, and that's what this guy right here is. Mass m. I said a moment ago that that was 13.9 grams, so we can say 13.9 Gs. We need to convert that into kilograms, and there are exactly 1,000 grams per 1 kilogram. Okay, so that looks like this: 1.00 kilogram per 1,000 grams. Okay, once again, if you're looking at units, we have grams on top here, we have grams on bottom here, those cancel. Okay, and so these guys multiply out. You end up, as it turns out, with 0.0139 kilograms worth of mass. Okay, and then you have some time. So that is the basic of the unit conversion that you're doing. Now for simplicity, what I need to do, is show you how to do this on a spreadsheet, because ultimately you are going to be, I'm sorry, my spreadsheet's going on the wrong thing. Let's move the camera over to here so that we can look at the screen that I'm working on. Okay, there we are. All right, so we got a spreadsheet for ourselves. Let me put this out of the way. We have a spreadsheet for ourselves, and what you're going to want to do on this spreadsheet is basically record whatever masses, times, etc. You've got in the experiment. Okay, so let's say, for the sake of argument, that I go through and I am measuring displacement versus period. Okay, so I started with a displacement of 2. You might actually want to start with a smaller displacement initially. It depends upon your spring set, depends upon the masses you're using and that kind of thing. Let's say that you have, let's type out displacement here, and then you really want to have units in here, like so. And I'm making 2 columns, one in centimeters because I measured stuff in centimeters. So maybe it's like 1 centimeter, 2 centimeter, 3, 4, 5. Maybe I've picked out my mass set so that I can get all those. Okay. Now you could by hand go through here on this, and let's actually zoom in a little bit. I could go through here by hand and use a calculator or just mental math it, see that 1 centimeter is 0.01 meters. So I could go in here and type in 0.01, 0.02, etc. And I could just keep doing that down. But one of the nice things about using Excel or OpenOffice or LibreOffice, this one is actually LibreOffice, but all 3 of these will do this for you. You can use the equation editor function to do these unit conversions for you. Okay, so the way that works is I come over here to this cell. I start off by typing an equals sign. Okay, that tells it that we're going to be putting an equation in and that it should calculate the result of this equation. And what I'm wanting to do is take this number right here, and then since I'm converting from centimeter to meter, as per this calculation that I've done here, I have to multiply by 1 and divide by 100. Well, multiplying by 1 could be an extra step. If it makes you feel better, you can put times 1 divided by 100, like so. All right. So the little star key, Shift 8, the little star, that's the multiplication symbol. The / key is the symbol for division. Okay, so if I hit enter, I get 0.01. Now, instead of doing that for every one of these cells and typing that in like this, if you highlight all the cells that you need to fill in, and on a Windows machine you would push Control and then the D key, the letter D for down, it will fill in all of those cells. And I believe it is also Control D on a Mac, if you're using a Mac machine. I don't know offhand what it is for Android, but if I assume it's probably the same or similar keystrokes. Okay, I'm going to actually undo what I've done. For what it's worth, that's Control Z, and I'm going to hover this right over here. You see how it changes from an arrow to a crosshair? If I click and drag down, you can see kind of like a magenta outline covering all those cells. And then if I unclick, it does the same thing as Control D. So that's another way that you can do this. And again, I know this works on both Macs and PCs, and I assume that, for example, Android devices, if you're doing this on a tablet or something, probably have something similar built in. Okay, so then you'd have like time. Okay, time is just in seconds. This is the time for 10 oscillations. Okay, so this is, we could say 10 oscillations. And by the way, you don't have to use 10 oscillations. You may find that it's more convenient to use 20. If the thing's really fast, it might be appropriate to use 20 oscillations rather than 10. If it's really slow, 5 might be okay, but I wouldn't go fewer than 5 unless it's really, really slow. You want the time frame of the interaction to be at least about 5 seconds. So I had 4.9 seconds. That's probably good enough. You want at least like about that. Any shorter and you may want to use more oscillations. Okay, this column will be the period. That's the time to do one oscillation. All right, so here I had 4.90 seconds. To get the period, what you do is equals, and again you select the cell, or you click on the cell, or you type the cell address, and then that was the time to get 10 oscillations, so you want the time for one oscillation, so divide by 10, and that will convert it. Now, I didn't go through and do the experiment for these others, but let's say that we did do it. Let's say that we get like 4.8, 4.8 again, 5.1, 4.7, 5.0, 5.1, something like that. Okay, so let's go through and basically convert everything like this. What you do next with these data is you want to insert a graph or make a graph. So I'm going to insert a chart, and basically what you do is, depending on what kind of program you're using and what machine you do, it's going to be under insert chart. You want an XY scatter plot. I usually go to data series, even though I'm only plotting one thing here. I add a series, I get the X values, so I'm going to need to pull this up so I can go over to where the X values are. Remember, we are looking at the period on the Y-axis versus this on the X-axis. So here are the X values. The Y values look like this. So oops, I didn't want that top one, so I got to reselect my range. Here are my Y values. Okay, so here's a scatter plot that it's created. Next, and then you should give it a title of some sort. So I'm just going to title this one Spring Oscillation Period versus initial displacement from equilibrium. Whoops, misspelled that. Equilibrium. Okay, so that's a fine title for this graph. You may have a different one. What did I put on the x-axis? I put displacement. Whoop. So I could put displacement, I could write out displacement from equilibrium, but since I've already said up here that this is displacement from equilibrium, simply saying displacement is adequate. I need to put some units. Remember, I converted all these to meters, so in parenthesis I put an M for meters. And then this one right here is actually average period. It's an average period because we let it go for 10 oscillations and then divide by 10. So that means that the average period of oscillation is 0.49 for those 10 oscillations. Okay, and then the unit for that is in seconds. All right, so then I hit finish and I have now a graph. And if you want to improve the graph a little bit, you can do stuff like tell it to put in a major grid so that you have your grid lines, or you can tell it to take the grid away so that it's just a blank space in here. You might, for this one and for the others, go in and what I want to do is format the y-axis here so that it goes all the way to 0. Because right now, looking at it, it just looks like random dots. But if I zoom out so that I can see where 0 is, these random dots actually fit reasonably well on a horizontal line. And in fact, you can insert a trend line if you'd like. It will, let's see, I'm going to go ahead and extrapolate backwards so it goes back, 0.01. And you can even tell it to show the equation if you'd like. This equation says that this line has some very slight non-zero slope, but it's not a very strong non-zero slope. Okay, it's more or less a horizontal line. So we would conclude if you have a horizontal line, and I'm actually going to ditch the equation now because I don't necessarily want that on the graph that I put into my formal report. But this horizontal line, we might say like this is more or less a horizontal line. You can even, if you want, come in and draw a horizontal line and see that they do line up pretty well. Like if I take away the trend line again, whoops, hello. If I take away this trend line and just look, I can see that this gray horizontal line at the 0.5 mark goes pretty well through them, and I can imagine another one that's parallel and just very slightly lower, like maybe 0.49, going through even better. And in fact, if you were to go back through and redo under the same settings, the same situation here, this one being 2 centimeters, having the same mass on here, which unfortunately we didn't write down earlier, and you do want the same mass for all of these, by the way. But if I put the exact same mass on everything and I repeat it, I may find that I don't get 4.9 again. It may be that repeating at 2 centimeters, I now get 4.8 or 5.1 or something like that. Okay, and so that means that in some sense there's actually error bars on each one of these. And you can actually, if you want to be really thorough, you could go back through and repeat this a few times. So, you know, what if I did in fact repeat it for 5 trials or something like that? This is kind of akin to what we do in the on-campus lab. Whoops. I'm going to move this over here. No, I'm not. excuse me a sec while I adjust these. Okay, this is akin to what we do in the on-campus lab. We actually do 5 trials of 10 oscillations each, albeit we do it with the pendulum lab. And then what we do is we'd have like another set of numbers. So maybe this is 4.9, maybe this is 4.8, 4.7, 5.1, 4.9, 5.1, 4.7. Okay, and then on the next one maybe you get 5, 4.7, maybe 5.1 here, 4.9, 4.8, and so on. Okay, so let's say that we do 3 trials maybe. So you can do the average of those 3 trials. This is the formula for that. You say equals average, and then you select your 3 trials that you want. You hit enter, you pull down like this, and now you have, maybe you say like this is the average. Okay, and then here you do standard deviation or error or something like that. And the formula for that is stdev, and then again you select the 3 and hit control down like that. Okay, so this would be like your period for one trial, again in seconds. This would be like your error in some sense. Okay, and that error, again, you can use this divided by 1, divide by 10 for the fact that these were error over 10. This becomes error over 1. There's a system for doing this called using t-scores, which is a bit advanced for this class. But for the sake of argument, we want to do something like this. Okay, and then we come over here, and what we can do is on these data points I can put error bars. Okay, I can make them positive and negative, and what I can do is I can use a cell range. And so basically what I do is just select and then again select and hit OK. Okay, and they're a little small. If I make this symbol a little smaller, then you can now see an error bar sticking up above and below some of these dots. Okay, so now imagine drawing a horizontal line that runs like this. That's maybe at 0.49 or something here. Okay, if you do that, you can imagine that line passing through either the box itself or basically every one of these boxes error bars except for maybe like 2 of them. So a horizontal line does fit this pretty well. Okay. So once you've done that, then the next thing is that you have to have the same sets of data for mass versus spring and for 1 spring and 2 springs. And instead of doing that for you, because again, I don't want to do the whole experiment for you and then people end up just fudging a little bit and taking the same numbers that I have. I know that a lot of you will honestly do the experiment. I also know from experience that if I put something in and say this is right, then this ends up showing up in people's formal lab write-up, and then it's like, okay, now I have to go through the whole why are you plagiarizing talk, and nobody wants to do that. Okay, so I'm going to show you the principle without showing you actual data. All right, let's say that I have some mass, and again, let's say that we put the mass in kilograms, right? And then over here I have the sorry, let's put this in grams. Let's do this. We'll put mass, we'll put it in grams here. We'll put it in kilograms here. Okay, and now let's say that we have time for 10 oscillations. Okay, and this is spring 1 in seconds, and this one can be spring 2, also in seconds. Okay, so in other words, I'm going to do this experiment twice, once on each of two different springs. Okay, and presumably I'm using the same mass. You could build this table to have, spring 1 mass time for 10 period, spring 2 mass time for 10 period. Whatever works for you. Okay, so now here we're going to say period. Whoops, I need to put period up here. Okay, and then again, this would be spring 1 in seconds and spring 2 in seconds. All right. So for the sake of argument, let's say that I happen to have masses that let me just increase in 10 gram increments. Whoops. So we can go this plus 10 and all the way down until I've collected enough data. Okay, this again should be this times 1 over 1000. Okay, and maybe it happens to go like this. Now let's say that I happen to have timed it and I end up with times like this. Maybe like this first one is let's say 5 seconds, and then this one right here ends up being 10 seconds. No, let's not make it 10. Let's make this 20. And this one can be 120 or something like that. And so on. All right, so I end up with my sets of times, and then of course I can do my conversions. So like this divided by 10, this one is that divided by 10, and I end up with some data. Okay, so now I'm ready to plot the data. I do the same thing as I did before. I bring in a chart like this, and I end up with this XY scatter chart just as before. This time I'm actually going to need 2 series, one for each of my 2 springs. I'm going to go ahead and give each one of them a name. Okay, so I have spring 1 series, and I have spring 2 series. Okay, the X values for both of them should be the masses involved, so I would select the mass category for both, so mass in kilograms. For the Y values, I need the period of oscillation in seconds, so I go and select those like so. I have to put in my title as I did before, so maybe the title now is period of oscillation for versus mass or oscillating mass or something like that on the end of a spring using 2 different springs. Okay, so I get a title like that. X-axis mass in kilograms, Y-axis period in seconds. Oops. Hit finish. Okay, so now I've got my graph. you can see that there are two sets of data on here. You can also see that these data are not linear. If I was going to go fit a line of best fit, so insert trend line like this, you can see that this line does not fit it at all. I mean, it maybe fits a very little bit, but it really on the whole does not fit. So what you have to do at this point is make a new graph. And on that new graph, you're going to need to essentially linearize this old one. And so what you will do is you could, for example, replot the y-axis. So linearization, let's redo the x-axis, replot the x-axis. So what we're going to do is take each of these and square them. Okay, so these are the new values that we're going to look at. You would make a new graph. I'm going to do it the quick way, I hope, by copying this graph, pasting it here, and then going in and basically going to the data ranges and changing what I'm plotting on X for each of them. So I'm changing the X's for each. Okay. And now I have something that's linear. I would maybe need to say linearization of period of oscillation versus mass on the end of a spring using two different masses. Okay. And so here, instead of mass, I would maybe need to say mass squared. So the units are now kilograms squared. Okay, and you can see that by replotting this way, if I insert a trend line, I now have a linear plot. It makes a nice straight line. Okay, it may be that you don't have to linearize x, it may be that you have to linearize the y-axis. Okay, so what would that look like? Basically what that would look like is, and you'd have a totally different set of data. So let me, instead of wasting your time by typing it each in while you watch, I'm going to type in a new set of data where you would have to linearize the other axis. Okay. All right. So new set of data. This time, again, these are not linear. You can see that they curve ever so slightly, and in fact, you can imagine a mass of 0 having a period of 0 to oscillate. So that exaggerates this curve that much more. To linearize this case, instead of linearizing x, you might linearize the y-axis. And what that's going to do is basically we're going to have to do one of these for each of the two springs. So this would be spring 1, here would be spring 2. Basically what we're going to do is just take the periods and square them instead of taking the masses and squaring them. Okay, now we come down here to this graph, and basically what I have to do is select my data ranges again. So I have to go back and get the correct X range. So that was again the mass. But now my Y value for the linearization is this column. And for spring 2, the X's again are the mass. The Y values are now this column. Okay. And we come over and you can see now it's again a nice straight line. Of course, we have changed it. It's no longer period. It is now period squared. So this is in square seconds. And this one actually just was the mass. So we can rename it as mass in kilograms. Okay. So you may have to use this process. If you get a horizontal line like this, or if you get a straight line the first time you graph, then no further analysis of the graphs via linearization is necessary. You're kind of done. If it's a horizontal line, then you say there's no relationship between these two variables. If it's a straight line, then it's basically like what you had in the Hooke's Law lab, F equals Kx. Okay. So at this point, I have walked you through basically the experiment, the experimental analysis, how to make the graphs, that kind of stuff. I'm going to go ahead, maybe one other thing to be said. If you click on the graph like this and just say copy, then you can, if you have just any old Word file, so like a Word document, you can in fact paste into the Word document like this, and then a Word document, so you can do typing to type up your report. Okay, so that's what you should do with those. You can in principle do the same with your data tables if you need to do that, or you can just insert a table into the Word document and type it that way. Okay, so I'm going to close this. I'm not hoping to use it any further today. Let's open back up our instructions, which are on the wrong screen. Okay, so I've basically, I've walked you through all of these, like all the instructions of the experiment. You are supposed to be making for yourself some predictions at the start of the experiment, like what is this going to depend upon? Is period going to depend upon amount of mass? Is it going to depend upon initial displacement? Is it going to depend upon the spring constant? And notice, by the way, with that graph, and so I guess I do actually need one thing here, which is that graph. You'll notice with this graph, there are two springs shown on the same graph. They clearly do not make the same line. The periods for all the red ones are shorter than the periods for all the blue ones. In other words, spring 1 has a faster period than spring 2. You would need to know which one has the greater spring force constant and what the ratio of those force constants is. And that's necessary for this lab as well. Okay, so I've already talked therefore about the nuts and bolts of how to do the experiment. Now I need to talk a bit about the sort of expectations of what it is that you're going to be turning in at the end of this experiment, because it's different from what we've been doing in every other lab. Troy University has introduced some guidelines that say that the General Studies program needs to essentially educate and empower students to become effective written communicators and critical thinkers. And so they've said that in science, the way that we're going to do this is require a formal laboratory report. So you, this time, instead of doing what you've been doing, which is do the lab, maybe take a picture and submit it to the discussion forum, take the quiz after the lab. Now, instead, you will write up your results of your lab. Really, you'll write up everything, your procedure, your results, your some discussion of the results, any conclusions, that kind of thing, as a formal lab report that you will then submit to me via Canvas. So because this is a sort of a bigger assignment than normal, or a much longer assignment than normal, I should say, therefore I'm not going to have a quiz this week on the lab, because this is going to take more work, I think, than just doing a quiz would have taken.
So what I have shown here on the screen is actually just the rubric that they originally handed to us to grade these, and there's some further rubrics, but effectively they come to the same thing. There are 6 categories that I'm supposed to grade in this thing that you're handing in, and I'm supposed to rate you as one of these 4 sort of levels, I guess you could say, for each of those categories. So it's possible that you have not addressed or not attempted the category at all, or barely attempted it. There is a novice level where you've kind of mentioned a few of the major points, but you've also missed at least a few of the major points within whatever category. And then it's sort of the expectation is that we want you all to be at least intermediate, let alone proficient. So intermediate basically means you could think of this as good enough, whereas proficient is you've really done well on this category. And the categories basically involve an introduction, and for that you're supposed to basically be giving me background information on the lab for the week. Okay, so if you read through what I've got here in each of these criteria, essentially it's telling you what you need to do in order to hit each possible level within the introduction. Okay, so not addressed says very little background information is provided and or information is incorrect. And novice, certain major introductory points are missing, meaning there's no background or there's no theory, there's no science or context or whatever. Intermediate essentially means like you've covered all of these and most of the major points, but there may be some aspect of the experiment that you don't cover, or there may be some vagueness or arbitrariness in some of the stuff that you state. Like maybe you decide to make predictions, so you say, okay, I have my spring, I have my spring and I have my mass, and I attach some mass to the end of the spring. I set it oscillating, then I time the period, and then I repeat but with more mass. And so maybe your prediction is just more mass means bigger period. Okay. Well, that is a prediction, and so in some sense it's like technically you have addressed that point. You've maybe technically mentioned the theory, but you haven't done a very good job of explaining what the theory says in this case. By which I mean, let's say I double the amount of mass. If I double the amount of mass, and the result is that the period is now half again as big as it was before. So, maybe it moves from 1 second to 1.5 seconds. I could say this has increased. The period has increased when I've increased the mass. But similarly, if I double the period I double the mass and the period doubles, then I would now say the same thing. Yeah, making the mass bigger means the period gets bigger. And if the period gets 4 times longer, well, again, same thing. Increasing mass increases period. It's too vague of a statement to distinguish between those 3 cases. Contrast that with stating as your theory something like this. I expect that when I double the mass, the period will double. Okay, so there I've made a particular kind of prediction. Double the mass, double the period. So if I change from a mass of 45 grams, let's say, to 90 grams, then if my period at 45 grams was 1 second, my period at 90 should now be 2 seconds. Okay, so I've made a very particular prediction there, which I can then test. Note that the more particular your prediction, the better the odds are that you can get it wrong as well, right? If I just said the vague statement, more mass means bigger period, then there's only two ways that I can really get it wrong, right? I can put more mass on there and find, to my surprise, a shorter period, or I could put more mass on and find the same period, and that's it. If it's not one of those two things, the only other option is it's a longer period, and my prediction is correct, but it's not a very specific prediction. It's not very particular. Now, if I say doubling the mass will double the period, then when I double the mass, when I go from 45 grams to 90 grams, there are many ways for my prediction to be pretty wrong. For example, my period might change from 1 second to 1.4 seconds. All right? So my prediction's wrong in the sense that I said it should double and it didn't. It only went up by 40%. Or if my period actually goes up to 4 seconds, it quadrupled, not doubled. So my theory is wrong, but it is a more particular theory. Now, part of getting from here, this intermediate stage, to the proficient stage in doing your introduction section is that your predictions need to be made. They need to be made thoroughly. They need to be particular. They need to be of the sort that says double the mass means double the period, or alternatively, double the mass means half the period if it's the other way around, right? And then it needs to be correct. Okay? So you would need to in fact see it double. The other thing is, if you look at what it says under proficient, it includes all the relevant science. It's got to put the experiment into context, or provide context for minor points. It provides context for major points. In this particular lab, the one that you are doing with the spring, you can put it into context by discussing other labs which you have done that are related to this one. For example, you have measured the period versus length and mass and initial displacement for a pendulum. So this experiment should consider some of what you saw in that other experiment. Likewise, you did a different experiment where you built a spring scale. Today's experiment should consider some of what you did when building the spring scale. That's putting stuff in context. Okay. Let's move on to the next couple criterion. There's a methodology and experimental design part. Basically, this is where you are, let's say you took a picture of your setup. You could include that here if you'd like. You would need to definitely include some procedure, such that if I read the procedure, I can duplicate what you did. Or if one of your classmates reads the procedure, they can duplicate what you've done. Okay, and so that's this methodology and experimental design. And again, this right here is sort of like the goal in some sense for everybody, and this is the absolute ideal. Okay. And by the way, I have also loaded up some standards that describe all these. Um, these are the guidelines that I've loaded for you that tell you what font size you should use, what text, how stuff should be spaced, where you put title and author and all that. But if you scroll down a bit, you get to stuff like this. Okay, so methodology and experimental design, this is what you are doing. This right here is what the standard is for getting full marks in doing this. Okay. Next area is your results. This is basically your data. Okay. You can include data tables. Note that in this data table that I've made, here's a hypothetical data table. Everything's labeled. There's, correct units and stuff. Heights are in centimeters, that kind of thing. There is a caption for the table. The caption can be slightly smaller font and italicized. It should be single spaced, whereas the rest should be double spaced. Okay. Mostly you're going to be making plots. Okay. How do you make a plot? There are several ways. I think you should use LibreOffice or Excel or New Octave, something like that. And I can actually briefly show how to do that at the end of this video as well. But for right now, just make it on a computer. This right here is an example of a quite nicely done plot. It's actually, I think the plot is from essentially like this experiment, except for that now we use a second ball. So like maybe this is for one of these two balls, and then I take a second bouncy ball and drop it. Again, this is just like a hypothetical experiment. You are actually using a spring. Okay. Your plots, if they're linear, should have a line of best fit to them. You may choose to display the equation of that line of best fit on the chart if you'd like, but you don't have to. You can also just get it via point slope method or what have you, and discuss that in your discussion. Figures also need to have some sort of a caption to them, as well as a title, and then both axes should be labeled and a scale created. Okay, and if you plot more than one set of data on a given graph, you will need some sort of a key or legend over here that tells me what it is that each plots. So there are blue squares for a blue ball, there are red diamonds for a red ball. The little sticks above and below are what are called error bars. Okay, so here's what this says about results. Okay, so these are your standards that you are looking for here. Again, the thing that is sort of good enough, you should have an adequate number of figures, basically graphs, tables, etc., to show or showcase all the data that's relevant. You need to have proper titles and legends and scales and axes labels and so on. If you're doing any kind of calculations here, you need to show the equation that you're using for the calculation and sort of like walk through the steps of how to do the calculation. If it is to be sort of proficient or highest marks, all of that, and then your results should have some nice logical sequencing. There should be sample calculations with correct equations, significant figures and units should be all correct. And yeah, that's your highest mark for this category results. Okay, so now we're halfway through the criterion on this. Next up is discussion. Okay, so the discussion here is basically looking at the data and maybe at your theory as well, and saying, this is what we observed and this is what the data means and this is how it compares to the theory. And this is why the data and the theory don't match perfectly. In other words, this is our error analysis. And if you have some unexpected results, you should maybe explain why they are there, or highlight them and say this is what these unexpected results imply. And then your standards here for that, your good enough standard. For some reason I can't just highlight one cell in the table. Basically just says you are allowed to lack a little bit of clarity, but they kind of give a very negative standard, to be honest. They don't really tell you what you have to do. They just say this is what you don't have present. Okay, so that's why I've given you this guideline for what you are supposed to do. Okay, and so then the thing that's been handed to me tells you here's what not to do, or whatever. Then the conclusion, basically, you should have a brief summary of your experiment in the conclusion. You should basically cite the actual data that you got and then explain this is what it means. Essentially, you can suggest further work. You can discuss any major sources of error or inconsistency, and then discuss whether or not that invalidates your experiment. If there happen to be some additional questions that are now posed now that you've done this experiment, what are they, and how might you try to answer them? Okay, so again, they've given sort of a negative set of standards to follow for everything but the highest marks. But you're shooting for this, and this is sort of like acceptable. Finally, we come to the writing quality part of the formal lab report, which for some reason is the longest part of it, because apparently this is the part that the powers that be want most to be hammered. Look, I'm not an English professor. I'm not looking for flowery writing, and I really don't want you to pad out the length of this report any longer than you need to in order to get it done. That said, you should be properly labeling and captioning stuff. You should say what needs to be said. You should use whatever vocabulary is relevant for the experiment. In this case, you should maybe actually talk about spring constants, not just how stiff the spring is, how bendy the spring is, that kind of thing. Use actual terms like spring constant, period, not just how much time it took to do the thing, or how much time does it take to do an oscillation is what a period is. But sometimes people will write, oh, this is just how much time it took to bounce up and down. No, just say the period. You should basically be free of grammar, syntax, spelling errors, that kind of thing. Check for typos, proofread it, that kind of thing. This is also the grading the how you've broken up the lab part of it. This document is not a single long essay unbroken by subheadings and so on. You really should have subheadings like this, and they can be set aside by underlining them or by making them bold or by both. maybe by having a little space between the end of one section and the beginning of the next. All of that is part of this. Also, the paper should be readable, relatively easy for me to read. It should be well organized, should follow a logical progression as you go through it. Okay, so that is the standards that I'm supposed to be grading this thing on. Now, as promised, I should probably review briefly how to make a graph.